Okay. I hear some echo.
El teu micro.
Sí, però jo l'he parat.
No, el micro.
No, el meu micro està parat. Now it's okay? Okay, sorry. I were my speakers. Okay, so welcome everybody. Thank you for joining. We are going to start this panel on runtime systems for Zettascale. I'm Rosa Badia from the Barcelona Supercomputing Center. Okay, so, well, when we proposed this panel, we said, well, exascale is around the corner, although we've seen this week that still waiting, okay, but almost there. This is the top 500 list published this week. It's almost, at least the positions I'm showing in the screen are the same as we had in June. But in any case, it's coming, no? And so we've seen that most systems had opted for heterogeneous architecture, and implying an exponential growing memory also, storage and computer power. We have seen during these years in preparation a lot of activity and convergence on advances in co-design, modeling and simulation, convergence with data analytics, machine learning, artificial intelligence. And there are a lot of expectations on what exascale will bring, with expected breakthroughs in many areas of science, material science, manufacturing, chemical design, artificial intelligence and machine learning, or areas of medicine like cancer research and treatment, or areas of urgent computing like assessment of earthquake or volcanoes, nowadays very in the news in my country, for example. So, well, there has been also a lot of activity in projects. No, here, sorry that I add this slide because this project is funding my travel to SC. So this is for an example of the activities we have towards the exascale. No? In this case, delivering a workflow software stack for the convergence of applications that combine HPC and data analytics, okay? And with targeting federation of HPC infrastructures, no? And giving services to scientific communities and engineering communities, like in this case, engineering, manufacturing for engineering with the pillar 1 that we have in the project, or climate, another pillar we have, and urgent computing. Okay? But there has been many of these in the different regions, no? In the States, in Japan, in many other of the countries. No? But then, given that we have been doing all these activities and we are here, no, with already this exascale, we are thinking what will be next. No? It's a bit early maybe, but it's always nice to start thinking about the future. And, well, predicting the future is difficult, okay? But what we think will be a Zettascale machine, no? So we have this 10 at 21, which is the next goal. And can we predict how these machines will look like? There has been people saying that there will be nodes much more diverse and heterogeneous components with different types of specialized accelerators, including new paradigms as quantum computing. No? For example, at SC, we've been seeing many different workshops, tutorials on quantum computing software. Also, we think that these new systems will pose a lot of scalability issues and limit the type of parallelism that can be exploited. No? And at the same time, also the same way that for exascale, the applications have been growing and new type of workflows have been appearing, also we can expect that this will continue growing in size and complexity. And that in order to be able to leverage the computing infrastructure that will be coming, no? And enable the progress in the different areas of science and technology that have been doing until now. No? And between the components of the software stack that we think that are relevant, we think that the runtime is one that can be critical, no? Due to the fact that we will have so many components to coordinate and orchestrate. No? So for this panel, I have invited these panelists today, all of them experts in different flavors of runtimes and programming models. Okay? We have Rajiv Thakur from Argonne National Lab. We have Samuel Thibault from the University of Bordeaux in France. Mitsuitsa Sato here in the room from Riken, Japan. Dide Munat from Kos University in Turkey. And my colleague Vicente Beltran, also here in the room, from the Barcelona Supercomputing Center in Spain. And initially, I have asked these questions to them. What do you think will be the major challenge or challenges for the runtime system for these new Zettascale machines? And how do you think this current runtime will evolve to deal with these challenges? Also, if they think if there will be parts of the runtime that will be moved into hardware, okay, in order to achieve the challenges of scalability and, sorry, it's working? Yeah, okay, sorry. I could not hear myself and I thought it was not working. And also which parts actually of the runtime systems they think that can be accelerated in hardware, okay, in order to reduce overheads that they will have. Okay, so the session will be organized first. The speakers in this order will present their position, okay, and they will try to answer the questions that I have asked them. Then I will also collect questions from Slido. I will collect only questions from Slido. We will not be circulating the mic in the room. And the different speakers will be trying to answer the different questions. So I will stop sharing. And Rajiv, would you like to start your position?
Yes. Let me just get my slides here. Do you see my slides now?
Yes.
Okay. I'm Rajiv Thakur from Argonne National Lab, and thanks, Rosa, for inviting me to serve on this panel. So we have reached, or almost reached, exascale computing with mostly incremental updates to runtime systems. And that's because the exascale systems themselves, or the architectures that they're based on, are mostly incremental updates to the Zettascale or the previous generation of systems. And also the programming models being used at exascale are either the same or similar ones with some improvements or incremental changes. So the runtime systems have not needed to make any dramatic changes to get us to exascale. However, going forward for the next 1,000-fold leap to Zettascale, runtime system designers are somewhat handicapped in a few ways, and the main thing is that they don't know what a Zettascale architecture will look like, and that's a fundamental thing that they need to know. There haven't been any point design studies of Zettascale that I'm aware of or that are well known as such. The power challenges of reaching Zettascale are daunting. That is, having a system with a power budget that anyone could afford to pay is a serious challenge. So we don't know what really a Zettascale would look like. There was some news about Intel aiming for Zettascale in 2027, but there were few details there, so I don't know. Also unknown is what the Zettascale programming models would be for these architectures. And the runtime sits between the programming model and the architecture itself, so both are somewhat unknown. And even applications themselves, we don't know whether they would be similar to today's applications, which are a mix of simulation and deep learning, AI type applications, or there will be a lot more, a greater proportion of applications that have complex workflows of AI-based steering type of codes, which require a different kind of programming model and a workflow type of system. So the main challenge is designing for the unknown. But the best one can assume, based on what we know today, is to expect a lot more heterogeneity in the nodes a lot more than there is today. So today we see nodes with GPUs and one kind of accelerators. A Zettascale node would perhaps have multiple types of accelerators, both general purpose and more specialized, that do specialized functions. There could even be quantum or neuromorphic accelerators, all on the same node. And to support such complex nodes and their associated programming approaches, the runtime system would need to be highly dynamic and adaptive. It would have to marshal resources and schedule tasks on these diverse accelerator types and know what these types are and their way of programming them and sort of schedule tasks on them. And it would have to be very efficient in moving data among the different types of memories that these devices use, and also between those memories and the network. So those challenges which are there today, they will just be greater at that scale. And in addition, the designers of runtime systems would need to be agile or nimble enough to respond to unanticipated changes in architectures, because it is quite possible that a Zettascale system would look something different than what we might imagine today or what we could guess going forward. So they need to adapt to changes as they happen. And also changes in programming models. It's quite possible that there'll be the programming models may also be different at that scale, and they would need to support those. So that's all I want to say in my initial comments. I look forward to discussing this topic with my colleagues on the panel and answering questions from the attendees. Thanks.
Thank you very much, Rajiv.
Let me stop sharing, yeah.
Yes. So Samuel, if you want to present your position.
Yes. Can I share my screen or yes? Okay, so you see my screen?
Yes.
Okay, so I am Samuel Thibault from the University of Bordeaux. So I wanted to talk about the problem of the ever-increasing number of nodes in such a system, because you want your application to scale to these nodes, and that means telling each node what it has to compute. And this requires a scalable way of expressing that, what should do what. In StarView in Bordeaux, but also in other runtimes like once in Spain, we have been using a sort of implicit distribution of the task graph. That is, the application doesn't have to tell which node exactly has to do what. And the problem is that then it's the runtime which does this, and this can have a high summation cost. You can decentralize the cost to reduce the amount of cost that this brings, but that's still possibly quite expensive. On the contrary, you have other programming models which let the application decide what should go where, like Cham++, in which you can be really assertive on the distribution. And you even have programming models where the placement is algebraic, actually, so like parsec. And we have seen some kind of hybrid ways of doing both of sort of implicit and possibly algebraic. So we have index rooms from the Legion people, which is interesting because they try to leverage both ways so that it's not too complex to program, but at the same time, it scales well because some part of the description is algebraic. And I was thinking, maybe we can leverage compilers to do some analysis for us so that some part of the distribution is algebraic, but it's deducted by the compiler from the source code itself. So that's one point I think is important for scaling to a large number of nodes. Then there's the problem of the faults. in Bordeaux, we started looking at this, making sure that we can deal with faults in an uncoordinated way so that it can scale. So it's not a question of doing a checkpoint for all the system at one time. So we've been working on uncoordinated checkpoints, or rather implicitly coordinated, because we have the task graph, we know the task graph, and we can let each node know which piece of data it has to save to the checkpoint. And so when it gets restarted, we know what to restore on the replacement node and which message to receive and send to the other nodes. And this without any global coordination, explicit coordination. And eventually, can we leverage some hardware for large systems? So we have seen with CUDA graph, for instance, a way to let the hardware manage the tiny tasks that we have, so that we can just delegate this to the hardware, so it knows the dependencies and handle them at really fine grain. We have also seen in the past years the notions of hierarchical task graphs, so that at the highest level, you only manipulate large pieces of task graph without looking at the details. And then it's only at the small nodes that you actually look at the details of the task graph. So this is, I think, a really promising approach. And eventually, maybe you could use artificial intelligence to do some scheduling. So we started playing with this in France between Lille and Bordeaux. And we could do this on the GPU to get the scheduling decision in just a snap. That was all I had to say for now. Let's discuss then. Thanks.
Thank you. So now I will play the video from Sato. Mitsuhisa Sato, sorry. Sato-san. Share advance video.
I am Sato, Riken Center for the Computational Science. I'm going to present my position talk for the panel runtime system for the Zettascale. I'm sorry I cannot respond to the Rosa's question, but first of all, I'd like to ask the question, is the Zettascale system is possible to build? If so, what does the Zettascale systems looks like? If the Zettascale system means that zettaflops, Zettascale systems are almost impossible to build due to the limitation of the power supply. The exascale system, exaflop system, needs to the 50 gigaflops per watt under the 20 megawatt system power supply. It is almost achieved by the GPU in a Oak Ridge system frontier. The other FUGAC system, the system is the half-wake exaflop system. Many core-based system is operated by around the 20 megawatt without the GPU. Zetaflop system requires more efficient, 1,000 times efficiency. That means that we need the efficiency at 50 teraflops per watt or 10 teraflops per watt. Bad news is that the progress of the silicon technologies, that means that the Moore's law is getting slowed down. I'm especially worried about in the price of the transistors will not go down not so much. The chiplet technologies are very interesting, but such technologies can increase the number of cores and enables the integration of the various accelerator, but it does not essentially improve the power efficiency. Special architectures like a PIM or application-specific architecture will improve, but I don't know. Let me Zettascale system defined as some system beyond the exascale, then the possible Zettascale system that is not a Zettaflop system will be as follows. The integration of the many kinds of the accelerator technologies such as GPU and FPGA. And the deep learning accelerators, application-specific accelerators. So these accelerators is attached to the node of the large-scale system like that. And another form is that the cluster of the various kind of the accelerator and special machines such as the quantum computers, something like this. So sometimes this kind of system is called a modular computing system. And network of the middle scale exascale system is another form of the Zettascale. That is a kind of exascale grid of the exascale system. So Zettascale runtime should support the various kind of the task offloading. The one thing is that the offloading within the node, offload to the GPU and the PCA, many kind of accelerators using the common API such as the OpenCL. So host has a lot of many kinds of the accelerators like this. And sometimes the offload to the SIMD as accelerators, even in a mini core system, is one of the candidates for accelerator. These should be supported by the common and standard program model. So like Cocos and One API and the DSLs. Another form is that offload outside of nodes. So that support the cluster of the various kind of the cluster. So something like this. So and offloading the clusters of the accelerators can be supported by the task parallel programming. So that can be used for the modular supercomputing. So last one is that the grid of the exascale computer. And this kind of the supercomputer is can be supported by the global task programming model or workflow over the network slice for the grid exascale system. So something like this. The slice is supported by the virtual the VLAN, and the job is consist of the set of tasks or program running on the slice of the network in the main system over the VLAN in a global network. So, and runtime need to interact and manage and resources in a slice. So, and we need data management to realize the concept of the data continuum. This is a very important concept of the big data and AI application. Thank you.
Thank you. Do you want to add anything else at this moment? Okay, so then I would like to invite Didem to present her position.
Okay, can you hear me fine?
Perfectly.
Okay. You can also see my slides, I believe.
Yes.
Okay. Hi everyone, my name is Didem Nat. I'm a faculty at Koç University, and I would like to present my visions or my thoughts on Zettascale systems. I'm glad that I'm talking right after Sato because I will agree and disagree some points he just made a few minutes ago. Okay, so I consider actually the Zettascale systems being representative of post-Moore's era systems. So we may actually reach post-Moore era, and then we'll have post-Moore machines part of the Zettascale systems. So I think we have to solve the post-Moore's programming first to be able to design our Zettascale machines. I guess everyone knows that Moore's law is slowing down. It's extremely slow. It's not keeping up the pace in last 5 or maybe more years. So what we can say about today's system is heterogeneity is commonplace. And the other fact that we can say about programming on these systems is data transfers and communication is dominant in performance and energy consumption. So what can we say about future systems? In fact, these two facts will still hold in the future. We may not know whether we will have, we don't know whether we'll have quantum computers or neuromorphic chips, etc. But what we know, probably we will have heterogeneity will still be common, and data transfers and communication will be dominant factor in the performance and energy consumption. Okay, and if you look at the HPC applications, they're no longer traditional HPC applications. They include modeling, simulation, AI, ML, and data analytics. These are also driving the heterogeneity in our systems, because when we think of heterogeneity, I'm not saying just GPUs or FPGAs. Even within a single GPU, you have heterogeneity. You have mixed precision or a lower precision or tensor cores, etc. So those add complexity to your programming. So in terms of software challenge, programming today's systems, heterogeneous systems are already challenging, and it will be even more challenging to program the systems beyond exascale, because as you increase the number of cores or the devices that you program, you will not be able to tolerate any slightest bottleneck. Otherwise, your application will not be scalable. So you have to get rid of all the bottlenecks as much as possible. Instead of talking about the runtime systems, I would like to talk about the new execution model, because then you can build a runtime system on this execution model. So the common approach to program current accelerator is the offload model, because it's easy. You just say that I want this part of the code will be running on the GPU or on FPGA, and then it will return back the result to CPU, and the CPU will have the full control. But I think we will, for future systems, we need much lower cost way of controlling the accelerators. What we need to do is give autonomy to accelerators, and we can potentially remove the CPU or host from being in the critical path, because right now it is in the critical path. It's controlling everything, all the accelerators. But if we can limit the intervening from the CPU or the host, then I think we can have better scalability and much lower latency in our application. So this means that accelerators should be able to self-schedule their computation, communication. They should be able to initiate data transfers without the involvement of the CPU or the host, even synchronize without the involvement of host. So all of these, of course, require hardware support as well, and some support at the software level, so that it can be exploited by the application. For example, right now on GPUs, you can initiate the data transfers from the GPU side, so you can say GPU-initiated communications. But the cost for these should be much lower, so it should be improved. And one of your questions, Rosa, was about should we have a hardware support for the runtime system? I think we should. I don't know how, because I don't design hardware, but it would be nice to have a dedicated hardware for scheduling and triggering the initial work on the accelerators. Because right now we use CPU, which is actually itself I consider as an accelerator, because it can be very good at high latency jobs. But I feel like we are wasting CPU resource if we just use the accelerators, because it acts as a coordinator. But we can probably have a separate dedicated hardware, maybe much smaller than the current CPUs to do the scheduling. Those are my thoughts. I'll be happy to answer any questions after the last speaker. Thank you.
Thank you very much, Didem. So now I'd like to ask Vicente Beltran to present.
Thank you, Rosa, for inviting me in this panel. I'm Vicente Beltran from Barcelona Supercomputing Center. And for the last years, I have been working on the Nanosys runtime system. That is the runtime system that we have developed to support the OMS2 programming model. And I will go through the different components to identify the challenges that we are facing and that for sure we will face in the future Zettascale systems. So if you are familiar with runtime systems, or runtime systems have the very same components as many other runtimes. We have a task scheduler, we have a dependency system, we have a memory allocator to deal with many core and multi-core systems. We have APIs to integrate with other programming models, and then we have a specific support for hardware accelerators. So let me go through the different challenges. So the first one is performance and scalability. So it's clear that the number of cores are increasing, and that means that to solve the very same problem, we will have to split in many more parts, so we can fit all the cores. So with the current synchronization techniques, it's quite difficult to fit all the cores inside a node. Right now we have already hundreds of cores inside a node. And the usual pattern is that you have one core that is generating the work to fit the others, right? So on the right, you can see a trace. And on the bottom part, you see a trace of 44 CPUs. These are the CPUs, and the colors represent what they are doing, and this is time, right? And what we can see here is that there is one task that is creating, one core that is creating tasks, and the other cores are trying to get tasks from the scheduler. The problem is that there is not enough work, and the threads, the cores that are trying to get tasks, are interfering with the thread that is creating tasks, because the thread that is creating tasks has to enter inside the scheduler to add the task, right? And this is something that you might find on most of the current runtime systems, and this is a bottleneck for many of them. So one thing that we have done on our runtime is to solve this issue by decoupling the thread, the core that is creating the task, from the other ones that are asking for work. So I'm not going through the details, but we have developed some advanced synchronization techniques that allow the thread that is creating tasks to push tasks in a wait-free manner inside the scheduler, and then one thread inside the scheduler is able to serve all the other cores, right? And with that, we are able to manage tasks with much more fine granularity. So besides the scheduler, that is one of the critical points, another critical point is the dependency system. In programming models like OMPSS2 or OpenMP, if you want, we are generating a DAC at runtime, and we have to calculate the dependencies between the different tasks that we are creating and executing at the same time. This is a very complex issue, and our previous implementation based on logs was not able to deal with the fine granularity that we will need to support in the future. So we developed a weight-free dependency system that can scale much better. And finally, it's also very important, another component that is the memory allocator on the runtime system, because memory allocation, when you are doing scheduling, the dependency system and so on, all the memory allocations are critical because they have logs under the hood, okay? So you have also to take this into account. So another challenge that we have already commented on the other introductions or positions is that system heterogeneity is going to grow for sure. And that means that we are going to have systems with many accelerators, different kinds of accelerators, from traditional GPUs, FPGA, to custom accelerators. And that brings to the table two different challenges. In one side, we need programming models to be able to generate kernels that can run on these accelerators. And for that, there are mainly two approaches. We have OpenACC or OpenMP offload, where you annotate a sequential code and it generates optimized kernels that can run on the accelerators. Or you can leverage CUDA-C or OpenCLC, low-level programming models, to develop these kernels or optimized libraries, right? And with that, we have one part of the equation, that is the kernels that need to run on the accelerators. But the other important part is the data movements, okay? So if you have many accelerators and you have a complex workflow, you will have to move around the data. And it's very important to do this in a very smart way, okay? So right now, most of the applications use explicit methods. So these CUDA or OpenCA, they have explicit APIs calls to do mem copies from the host to the accelerator, or even from one accelerator to another accelerator. But this is enough for current applications that have a regular structure, but will not be able this will not scale to the next generation applications that are mixing HPC simulations with artificial intelligence or data analytics. So for that, one of the components that will be key will be the directory and cache. So most runtime systems will have to be augmented with this kind of technology that we pioneered at BSc like 10 years ago with my colleagues Rosa or Jesus. And this component is the one that takes care of transparently move the data when it's needed. And not only that, it's also providing hints to the scheduler to be able to optimize the placement of the kernels. And this is very important because even if at the programming model you can optimize some of the challenges related to data movements, these systems are very dynamic. And that means that you don't know at compile time what is the best distribution of the workload, because maybe your application are irregular or the performance of the different components are not the same. So the runtime system, one of the main points is to do this load balancing. And for doing this load balancing, you have to take into account the cost of the data movement. So the other major challenge is application complexity, as we have already listened on the other talk. So there is a convergence of HPC simulations, artificial intelligence workloads, and data analytics. And this makes things much more complicated because there is no one runtime anymore. We are combining many parallel libraries, many runtime systems. And if it is already difficult to instrument and to debug or visualize a standalone application, a workflow like doing in situ data analytics or a couple code, it's really difficult. So we need instrumentation and visualization tools to be able to understand how things are performing. And finally, it's also important to add tools to check application correctness. So it's very difficult to write correct parallel code, and this is also an important aspect of runtime systems. They have to be extended to help with checking application correctness and also debugging facilities. And finally, I think that this is the most important challenge that runtime systems will face is interoperability and composability. How we are going to mix together many different programming models, many different runtime systems, and make them perform optimally on those systems. So this is a challenge, but at the same time, is also an opportunity. So we have already done some work integrating MPI with the tasking model of OMPSS2 and OpenMP by, for instance, moving the progress engine of MPI inside the Nano6 runtime. So the Nano6 runtime is the one that from time to time checks and make progress of the MPI operation. And with that, you avoid oversubscription between the threads of MPI and the threads of the runtime and this kind of thing. So these kind of APIs are very important to be able to integrate other programming models with the several programming models together. Another important aspect is that runtime systems have to be augmented with introspection capabilities. That means that we should be aware if we are running a memory-bound application, a compute-bound application, what phase of the application we are executing, so we can then take more smart decisions about how we are using resources. So this is also something that we have on our runtime system, and that allows us to take more smart decisions about how we are using the CPUs. For instance, if we are executing a memory-bound application, and we have 48 cores on our node, probably executing only on 40 nodes is enough, and we get the very same performance because it's bandwidth-bound limited the application. So why we are using all the cores to execute that application? And this is something that we can realize without any application developer intervention, just by analyzing the application that we are developing. And finally, this is also very important for energy management. As I said, if we can execute application with 40 cores, why we should use 48? We can save some energy by doing that. And yeah, that was my last slide.
Thank you very much. Okay, so I've been looking at the different questions in Slido, and thank you very much. But before collecting some of them, I wanted to ask something as an answer to the position of Sato-san. No? So you've been very radical, saying that you don't think that Zettascale machines, as we think of a supercomputer, are not possible to be built. No? So I want to ask the others, no? What do you think if you think that such Zettascale machines can be built as the way we think now of supercomputers? Or do you foresee, as Sato-san, a system organization similar to what he proposed? Okay, I don't know if you want to.
So, as I said, if that Zettascale means that zettaflops, then I would say that it is not possible. But let me define the Zettascale system as the next of the exascale system. Then we have the many ways, so in a heterogeneous in a many levels. So we have to think how to program that kind of system. So offloading and the nodes, or offloading between the clusters, and also a kind of the grid of the some exascale system. It's mean that a kind of workflow programming. So, and I think recently I'm interested in the programming model supporting the stream. So at this moment, OpenMP and another programming model is successful to describe the offloading. But as I mentioned in another panelist, the offloading model is involved kind of the host involvement. But to make it more efficient, we need support more for the streaming programming between the components.
So I don't know if others want to answer my question about.
Yeah, I'd like to hear.
I don't know if you want to raise hand, and I can moderate, or if not.
So what is the exascale system?
That's it.
No,
System.
Zettascale system.
Vicente, do you have any position on this?
So the question is, what is the Zettascale system, or whether we will have a Zettascale system?
No,
Which one?
My question was that Sato considers that we will not see a Zettascale system as a current exascale enlarged. He thinks that will be composed of multiple slices of composing different separated systems. And so my question is if you agree with Sato, or you think that no, that will be possible, that the technology evolves and that we will be able to build Zettascale machines.
I mean, we can see different components, and I want to believe that we will see Zettascale, because we have to be hopeful and work on it. Otherwise, we will just go home, right? Not do the science. So I want to believe we will see, but maybe not in 10 years or 50 years. But I think we have to solve the post-Moore's law problem first in terms of architecture. Then probably we will see Zettascale systems, but it will take some time for sure.
Well, in this sense, I always remind people that when I was a PhD student, like 25 years ago or a bit more, I had a book that said that Moore's law will end very soon because we will not be able to build chips beyond 0.25 microns. So with this, after this, my expectations on the technology evolution have evolved a lot. No? I don't know, Rajiv, you want to answer? Sorry.
Yeah, I think it's also tied to this question that somebody has asked that 5-10 years ago it was claimed that exascale would require exotic solutions, but it has not panned out that way. Why is Zettascale different, or will it need exotic solutions? So I think it's the power challenge that's the problem. And if you need a Zettascale system in the traditional sense, you need some solution that to the power problem, so that one can build a system that one can afford to pay the bill for. And that's where the exotic technology may be needed. Otherwise, yeah, we could have a collection, or a loosely coupled collection of many exascale class systems for specialized use cases that could be considered as a Zettascale.
Okay, Rajiv, thank you for picking that question from Slido. I don't know if anybody else want to answer this question. I can repeat it. So it says 5-10 years ago, it was often claimed that exascale will require exotic solutions, but it doesn't seem to have panned out that way. Why is Zettascale different? And I wanted to add an addition to this question. If you think that there will be any disruptive aspect in terms of architecture, which will require a radical change in the runtime. And it seems, well, Sato, I think Sato-san has already put his position. I don't know. Samuel.
Yes, I wanted to strongly agree with Didem when she wrote that every little point of contention in the runtime will pose a problem. And we've seen that in the past already, but here with so many cores, so many machines, anything that is badly shaped with a loose algorithm or implementation, all the tiny details will matter. And that's really a problem. I mean, it's interesting to see that all different talks have focused on different kinds of questions, but in the end, a runtime will have to address all of them. And that's the complex matter. You have to do all of this, all of what we have published in the past, to make sure that the system actually scales.
Okay. Any addition?
So another challenge will be that we have no idea how Zettascale system will look like, and probably there will be many different research lines that will be very different apart. And this will be another challenge for runtime systems, because there will be no common path that we can just support that one. There will be many alternatives, and runtime systems will have to be adapted, and probably there will be tension because the design decisions will be very different. And I have no idea really how we are going to cope with that.
Okay. Any other addition to this? If not, there are a few questions about MPI, and what I will do is join them, read them, and then others can comment on it. So there is one about if you expect MPI plus X will still be the dominant programming model in the Zettascale era. And then a follow-up or another question is, how do you expect MPI to deal with the accelerators? If using MPI plus X models, no, it's not a question then. If using MPI plus X models often has issues with synchronization. And then there is also a question for Rajiv. Can you discuss challenges for MPI in scaling to Zettascale, assuming relatively high node heterogeneity as you are alluding to? So I don't know, maybe Rajiv, do you want to start? And
yeah, I can start. So MPI plus X will have a role to play. It may not be the only, it won't be the only approach. And we should think of it as not just MPI plus X, but MPI plus X plus Y plus Z, or whatever is needed there, because we will have many of these specialized device types or accelerator types on a node, each with their own programming approach, and MPI would have to play well or interoperate well with all of this. And MPI is just a communication library. It moves data around. It will move it across the network. It could move it within a node. And if some other library could do that, or a higher level approach could hide that would be fine. And we're already seeing other approaches being used, and there is room for other approaches as well.
So I have a question to the Rajiv.
Yeah.
So I remember for I/O, so MPI I/O is standardized, but I saw that not many advances related to the I/O. So is there any activity to support the I/O from MPI communities? So I think that this is very important to implement big data's application.
Yeah, so MPI-IO exists, and it's supported, and many of the higher level I/O libraries they use MPI-IO as their intermediate layer for doing the I/O. So you take NetCDF, the parallel NetCDF, or HDF5, or other approaches. So I/O is handled at multiple levels of the I/O stack, and MPI/IO provides an interface at somewhat of a file system level, or at that level of the stack. But there are approaches above it that provide features that applications want more than just raw I/O. They want some file formats and portability and so forth. So, yeah, so there's a lot of room for improvements in I/O at various levels, and there could be some updates to the MPI/IO spec as well. Right now, it hasn't changed a lot in a while. There have been a few small changes in 3.1, MPI 3.1, I believe. But there is room for updates there. One thing I forgot to mention earlier in that MPI plus, are any changes to MPI needed? So yesterday there was a paper at SC on QMPI, that is quantum MPI, or MPI for quantum algorithms, by Torsten and other authors from Microsoft. So those kinds of things would be needed. So if there's quantum gets more widely used, there might be some MPI support needed for quantum algorithms. So there's room for research in that dimension.
Thank you very much. So now that you mentioned this about quantum, there is a question about accelerators. Okay, are you expecting meaningful quantum computing-based accelerators within the Zettascale timeframe? And how would they be benchmarked? And then I would like to join it with another question that I think a bit provocative. Do you think a Zettascale application will have enough diverse computation to use more than 2 accelerator types? I don't know if any have any position.
I can take this last one. So I think that this is an inflection point. No? The complexity of the hardware is increasing a lot, and at the same time, the complexity of the applications are also increasing a lot. And that is a challenge, but at the same time is an opportunity. So if we are mixing HPC simulations with artificial intelligence things, with data analytics, then at the end we have more parallelism. We have more independent activities and with different characteristics. So that opens the possibility to use different accelerators in a different way, in a different ways. If you right now have an HPC computation and your main kernel is 95% of the time, there are not a lot of options. You optimize that on one accelerator and that's all. But if the application complexity increase, it's also an opportunity in that sense.
Also, I think if we go towards the direction that Sato-san was mentioning of workflows,
Yes.
there will be much more heterogeneous computations, workflows that will require this different type of...
So once that kind of accelerator is abstracted as the task, then we can combine them. Even we have the different kind of the accelerator.
So, and following with accelerators, the autonomous accelerators have raised some interest in them. So there are some questions for you, which also are related to what I was thinking, because I wanted you to ask you also if you think that there will be more distributed type of runtimes that can coordinate between them, and I think it's a bit your idea of the autonomous accelerators. Particularly, the questions say if you can, do you want better dynamic programming on the accelerators? This is one question. Then also they are asking you if you can clarify why we need autonomous accelerators, if it's to save CPU resources.
So, I think this is an alternative way to program. One way is, the offload model where the CPU coordinates everything, but in the autonomous acceleration, you can reduce the latency because you don't need to kind of handshake with the CPU all the time. And also, you can potentially improve the data movement because right now, most of the time, the data goes through the CPU, or you need to launch a new kernel, and then all the data you have in the memory on the GPU or another accelerator disappears. Your cache disappears. So when I say autonomous, I mean why not give a little more intelligence to accelerators so that they can actually communicate with other accelerators. Or they can offload if they have an extra work. For example, in the middle of the computation, I'm just giving an example, you may need some quantum computing parts. So does this need to go through the CPU? Can this accelerator take the initiatives? Okay, I need quantum calculation here. Can I just offload my computation to other accelerator? So I think we need to think a little out of the box to eliminate all the latency and data movement issues. And if we give a little more freedom, maybe to accelerators, we can achieve that. I don't think this is easy to implement because it requires hardware support, software support. But I think we should be open to this kind of execution model as well.
I think Samuel wants to add something.
Yes, offloading real parts of the software to the accelerators is really interesting. The key difficulty I see there is that we will need synchronization between what happens on the GPU and, for instance, messages coming from the network accelerating some other parts of the application. So for this, we would need a common way of synchronizing everything. At the moment, what happens is that the runtime running on the CPU does this. It collects the events from this and that and notifies the other parts of the machine. We would need a common interface, possibly a hardware interface, some part of the machine which centralizes the synchronization between the network, the GPU, and the disk or whatever. So possibly we need to define something standard.
Thank you. Any addition at this point? Okay, although already has been commented a bit, but maybe you can, some of you can comment on the criticality of the data movement. No? So the question says, data movement is going to be critical for the Zettascale. What do you see for the role of the runtime system in dealing with the I/O challenges and bottlenecks? Okay, Vicente, and then Samuel, I think you raised at the same time, sorry.
Okay, so as I said in my introductory in the position talk, I think that, and yesterday on the panel on programming models, everybody agreed that data movement is going to play a critical role. And I think that techniques like that, the ones that we develop to program GPUs, obviously extended and improved, are going to play a critical role. Because right now, if you have only the CPU and the GPU, the programmer still can think about, okay, I have my data on the GPU, how I can move to the GPU, how can I optimize that process. But as soon as the application complexity increases and you don't have one GPU, but you have a GPU, a custom accelerator, a signal processor, developing by hand the optimal path of the data movements is going to be very, very complicated and not even possible, because it's not a static thing that you can decide when you are programming the application, because the runtime is doing also the load balancing between the computing elements. And for that, technologies like the directory that tracks where data is and catch and automatically moving the data around, and also giving back information to the scheduler to be able to take these kind of decisions, I think that is going to play a major role. Whatever is the direction that the technology goes to reach Zettascale, we will need this kind of technology to deal in a transparent way, and probably it would be also something interesting to do some kind of co-design with the hardware, because right now we have unified memory, but everybody knows that the performance is not as good as it should be. So probably co-designing this kind of directory cache that we have in software with the current hardware support is probably one way that is worth to explore.
So another thing is, I'd like to point out that so for the global programming for the Zettascale, that is the kind of the combination of the exascale system on the internet. So supporting the digital continuum is very important. So that is the essential point of the data movement. So how to support storage and how to support a stream or something.
Samuel, sorry.
Yes. So I agree that we definitely want to make data transfers automatic. So we've been using a directory in SAPU indeed for a decade now, and people really love not having to care about the positions of the data. The co-design approach with the hardware didn't happen yet. We had some sort of try from Intel with the SCCS chips, because it didn't have coherence between all the caches, and so you had to flush the caches yourself when you wanted to do it. And that was interesting, because then you really tell the hardware, okay, now flush the directory, and you were able to control a bit of the hardware caching, and possibly that's a way that we could try to resurrect indeed, to make all of this more performant. But then we will have to care for scheduling. We've been playing lately with a PhD student here in Bordeaux with trying to reduce as much as possible the data movements and check how far we can go. For instance, with simple things like matrix multiplication, it's not so obvious, and we have some low bounds available, and we managed to get close to it. But we will really have to take care of this, monitor this, provide ways for the programmer maybe to check that we have managed to make the scheduler think locally and avoid transfers. So making transfers automatic is a first step, of course, but we have to strive for reducing the amount, of course.
I would like to add what Simona said. Someone asked what was the main difference between the runtime systems for Zettascale and for exascale. I think for exascale, we acknowledged the data moment cost much earlier and then design our runtime systems around this objective that data locality matters, so we should improve it and avoid data moment as much as possible. So I think we succeeded at least because we knew that data moment dominates, and in the future it will be again a problem because we still use electrons to transfer, but maybe photonics will be, we will be able to use it in the future. So this may change how we design our runtime systems.
Okay. So, moving to another topic, Samuel has mentioned the use of machine learning, no? And something that nowadays appears a lot, no? So, on one side, I don't know if we have enough training data for training machine learning, for doing some behaviors in the runtime system. And the other thing is if others consider this as an option, no, to add machine learning in the engine of the runtime, no, to take decisions, scheduling decisions, I/O decisions. I don't know if others have considered this. Who wants to start? So, no sé. Samuel?
Yes, we started playing with this. For now, it's really preliminary work. But we just feed the machine learning network with the information on the available tasks and dependencies. The training of the network can actually be done with simulation, not actually doing actual performance, actual measurements with real computations. We can just train it with the real task graphs, but simulated execution so that the network can learn quite quickly from real-world cases, but with simulated execution. I guess we will need to collect different kinds of task graphs so that the network can address different kinds of applications. Probably we will want to train different kinds of networks for the different kinds of applications so that somebody doing some kinds of science can use a trained network for his kind of science and his kind of applications.
So I don't know if others have considered this. Have you added this in?
Yeah, related to the first question about how to get the information, I think that this is where having these introspection capabilities inside the runtime is very important, because then you can gather a lot of information about the application that you are executing, the different tasks, if they are memory bound, compute bound. And we have not started to explore yet. We are using simple heuristics to try to improve the scheduling. But I think that is clearly a very interesting research line. Try to exploit the information that right now we are capturing where we are executing applications. We can save the type of the task that we are executing, the type of scheduling decision that we are done. And by feeding that to machine learning, I think that we could probably get better scheduling algorithms that can capture things that we cannot see right now. Because there are many things that influence when you take a scheduling decision. So maybe if the previous task has generated some data on the current core, it's a good opportunity to run there. But if at the same time on a core close there is also a memory-bound task running, maybe it's not that good option. And it's very difficult to capture all these things on a heuristic. And probably machine learning methods could help on that, on tackling all this complexity.
I don't know if Didem or Sato-san or Rashif want to add anything on this topic? No? Okay, so then there is a question about benchmarks. Will the classical HPL, etc., benchmark even remain meaningful at that scale? Or we will need to define new benchmarks? Or benchmarks not only that they compute, classify the machines with regard to the computing, no? For example, Green 5000 is much more newer than the top 500, no? Maybe we will need to do another type of classification. Any thoughts on this?
So I remember it's almost 10 or 15 years ago, so at the age of the grid computing, so community was going to make a kind of benchmark over the grid, but I don't know it is successful or not.
There is an initiative on workflows.
Yeah.
Also, workflows RI. And on some of the meetings we were discussing also the need for benchmarks, no? But yeah, it's something.
Yeah, it is meaningful.
And also, what Sato mentioned, if we have this modular supercomputer design, then a single benchmark will not stress all the different parts of the component. So you need to have. I don't know what kind of benchmark it will be. Maybe some mini apps, collection of apps, maybe will be tested. Not sure. Yeah, but HPL won't be sufficient probably if we have diverse set of accelerators.
Yeah, I agree that we need multiple benchmarks to reflect the kinds of applications that will run on the system. HPL provides one measure, and it's a hard to attain number that it provides because applications don't achieve that the number that HPL can achieve. But it does stress the system, and it's a test that the system can stay on and run HPL at least, because even that can be a challenge for a new system. But there's definitely room for additional benchmarks that will be more representative of the workloads that will run on the Zettascale system.
Okay, so to finalize a bit, there are multiple questions about if we really need this Zettascale machine, if there will be workloads that need Zettascale, which kind of applications will need Zettascale. So I think these questions were also asked for exascale, to be honest. And the evolution has bring us to exascale, no? So I don't know if anybody wants to make any comment on this direction. What is your opinion about it?
So, okay. So if the Zettascale system will be the kind of heterogeneous and a kind of combination of the many kind of the computer, so then application will be the more the combination of the many application. So that is the kind of the workflow between the certain size of the large-scale computing, I think. Though it's not single application anymore, I think.
You think not, but I think also was set for exascale. And,
Yeah, but I mean, we should ask this question to application people. And if you ask them, they always want more. So they will say, this is not enough, you want more. So if you talk to climate modeling people, for example, they want more. I mean, I cannot think of at the top of my head to give this as an application that will require Zettascale, but if you ask this question to application people, they say, yes, we will need.
okay. Any addition for this question? If not, I would like to start asking all the panelists for a final conclusion statement. No sé, Vicenç, I will do now in
Reverse order.
reverse order.
Okay.
So if Vicenç, if you want to say...
Thank you, because I have the most time to think about that.
No, but I told you in advance.
Okay, so I think that we are really in a very exciting moment, because in the transition to exascale, we didn't have all the limitations, all the technical limitations that we are facing right now. So that means that for sure this specialization, this heterogeneity is going to be a big challenge, but at the same time I think that this is a big opportunity. At the runtime, we have a lot of, at the runtime level, we have a lot of challenges. We have to think about the programming models. There is an explosion on programming models, so we have focused most of the discussion on the hardware and all the different things, but there is also a lot of developments on the software side, the development of new programming models, DSLs, and this is also a lot of challenge, but a lot of opportunities, and there will be a need of co-design between all the different layers. I know that this is a topic, co-design is always necessary, but at this point I think that it will be critical to be able to get performance from these future systems. Yeah, that's...
Thank you, Vicenç. Didem?
Well, I agree that it will be challenging, but challenging is also good because it gives us a lot of research ideas to work on and keep our jobs, right? So in the future systems, I think any bottleneck will hinder the scalability. So we need to get rid of any latency, any data movement as much as possible. And also we need to think of alternative execution models in addition to traditional ones to reach beyond, exascale computing. Yes.
Thank you. So, Sato?
Okay. So again, I'm old people, so I remember the time we started the exascale project. So at that time, we had a ESP, exascale software project, and the many researchers is like getting together to discuss what the system of the exascale. So at this moment, we are sure we can make an exascale computer, and the next year or the next year. So I'm sure the real exaflops computer is coming. But to be honest, for the Zettascale system, so I can imagine what's kind of technology make it possible. So as I said in my position talk, so Zettascale system is defined by a kind of next of the exascale system. So it will be the kind of a heterogeneous system which has the many kind of the component, the specialized devices, or the quantum computer, whatever. So to make use of that kind of system, I think a role of the programming model or runtime system it's more important. So I'm very looking forward to having such kind of very exciting ages. Thank you.
Thank you. Samuel.
Yes, it will be really a challenging time for the runtime CD to be able to keep up with the scalability and with so many cores, so many accelerators and nodes. Possibly we will have to rethink the inner workings of our runtimes to really completely rethink what the task is, what the data is. So with the directories, we were already able to make a data show up in several places. So like quantum data, it's in several places at a time. But that will be probably yet more things to invent to make the runtime scale. But then I would like to agree also on the programming model part. The question really is how do you express so much parallelism? How do you manage? I mean, not only do it, but do it in a maintainable way. Because you have physics example, chemistry application or whatever, and then you want to express this in a simple way so that it's maintainable. But in a very largely parallel way. That's a concern that we have.
Thank you. Rajiv?
Yeah, we've been so focused on getting to exascale that we have almost forgotten to look beyond that and look towards Zettascale. So it's good that we are having this discussion, and thanks, Rosa, for organizing this panel. We need to think about more than just runtime systems for Zettascale, though. We have to think about what the systems themselves would be, what the applications would be, programming models, and the whole stack. Similar to what we did for petascale way back in the late 90s, and for exascale about 10 to 15 years ago, and that's what got us here. And I think we need to have more of this conversation. If you look at the SC21 program, this might be the only event that even mentions Zettascale, and some people were surprised to even see Zettascale mentioned, and they even asked me about it. But I think we need more of this and more of it next year, and looking at all aspects of it. So thanks for organizing this panel.
Thank you very much. So then we'll...
Thank you, Rosa.
Thank you, Rosa.
Okay. I was going to say something else. as a bit as a conclusion, no? I think still we don't know how Zettascale machines will look, no? If it will have multiple accelerators, or if they will act autonomously, if we will continue having MPI plus X, or MPI plus X plus Y, or what I say, even I do comms plus MPI plus X, for example. So this will be the workflows idea, no? And there are many different aspects, no, that have to be discussed, and I think what Rajiv has said, it's very important, no, that we start brainstorming. I think this has been a bit starting point, no, at least from the runtime system point of view. My answer, if I can answer some of these questions that are reluctant about if there are changes, I think there are a lot of evolution in the runtimes, in the programming models. The tasks didn't exist some years ago. We were proposing them, and now everybody speaks about tasks and offloading tasks. No? So there are changes, although sometimes we forgot that, because this everything takes a time. No? So I think we have time still to prepare for Zettascale, to think what we need to do to prepare to whatever configuration of the Zettascale machines. No? And I would like to thank all my panelists for accepting to be in this. I think it's been a challenging topic. No? It's not easy to speak to something that you don't know how it will be, and how can we evolve our research towards this. So thank you very much for accepting, and hope had been interesting. Also, thank you very much for the audience for attending, both that are in the room and all those that are remote. So thank you very much, and hope we can have another meeting talking about this next year in a BOF or a workshop, whatever it's more relevant. Okay.
So thank you for those.
Thank